Hello students, in this video we will discuss the working principle of Colpitts oscillator and also we will derive the frequency of oscillation and condition for oscillation. Colpitts oscillator is a type of LC oscillator which produces sine wave in the range of radio frequencies. Hence it is coming under high frequency oscillator or radio frequency oscillator. Colpitts oscillator consists of the amplifier stage and feedback network or frequency determining network. A LC tank circuit forms the feedback network, which is also called as tuned circuit or resonating circuit. Colpitts oscillator has two capacitors and one inductor in its feedback network. The amplifier stage uses a transistor as an active device in common emitter configuration. The potential divider resistors R1, R2 and emitter resistor RE are providing necessary biasing to the circuit so that transistor can operate in its active region to amplify the signal properly. RFC is the radio frequency choke which has very high reactance for high frequencies, so it can be treated as open circuit. While for DC conditions, the reactance of the RFC choke is 0, so it allows DC to pass through it and blocks transient AC signal. Hence it provides isolation between AC and DC operation. CE is the emitter bypass capacitor which is used to avoid the negative feedback given to the circuit. CC1 and CC2 are the coupling capacitors. CC2 is used to couple the output of the transistor amplifier to the feedback network, whereas CC1 is used to couple the feedback signal to the input of the transistor amplifier. The common emitter amplifier stage provides a phase shift of 180 degree. As the emitter is grounded, the base and collector voltages are 180 degree out of phase with each other. As the center of the capacitor C1 and C2 is grounded, the potential at the point A is 180 degree out of phase with the potential at the point B. Hence, the feedback network also provides an additional phase shift of 180 degree. Thus, the total phase shift around the loop is 360 degree or 0 degree, which satisfies the required condition for oscillation. When the power supply is switched on, the capacitors C1 and C2 start charging towards VCC. Once they are completely charged, they start discharging through the inductor. Because of this, current flows through the inductor. Due to this current flow, a magnetic field sets up around the coil. Once they are completely discharged, the maximum current flows through the circuit. At this instant, the electrostatic energy is converted into magnetic energy. Now, the magnetic field around the coil starts collapsing. As per Lenz's law, a back EMF will be induced, which charges the capacitors with reverse polarity. Once they are completely charged, the magnetic energy is converted back to electrostatic energy. Now the capacitors start discharging through the inductor once again, but the direction of the current is opposite to that of the direction of the current earlier. Once they are completely discharged, the electrostatic energy is converted into magnetic energy. This process repeats. Thus, charging of capacitors with alternate polarities and discharging produces alternating current, but the amplitude of the signal is very low. The voltage across the capacitor C2 is applied as the feedback signal, then it is amplified. Once again, the amplified signal is applied to the feedback network, and this process is continued so that the circuit adjusts itself to get A beta equal to 1, resulting into sustained oscillations. To understand the working of LC tank circuit with step-by-step diagrams, you can refer my earlier video named Working of LC Tank Circuit. Now let us write the general expression for LC oscillators to find the frequency of oscillation and condition for oscillation. To learn the derivation of this general expression, you can refer my previous video titled General Equation of LC Oscillators. As we discussed, in Colpitts oscillator, Z1, Z2 are capacitors and Z3 is an inductor. Substitute Z1 equal to minus J by omega C1, Z2 equal to minus J by omega C2 and Z3 equal to J omega L in this expression. Here H of E is written as it is. For Z1, minus J by omega C1 is substituted. For Z2, minus J by omega C2 is substituted. Plus Z3 is replaced by J omega L. Z1 is replaced by minus J by omega C1 plus Z1, Z2 are replaced by minus J by omega C1 into minus J by omega C2 plus HIE into for Z1 minus J by omega C1, for Z2 minus J by omega C2, for Z3 plus J omega L are substituted. Here J into J is J square, which is minus 1, minus into minus plus, plus into minus minus h of E divided by omega square C1 C2. Here omega is getting cancelled in the second term. J into J is minus 1, minus into minus plus L by C1. Here J into J is minus 1, minus into minus is plus, plus into minus is minus 1 divided by omega square C1 C2. Here we'll take J commonly out between these three terms. So this term becomes J into HIE into minus 1 by omega C1 minus 1 by omega C2 plus omega L equal to 0. This is the real part of this expression and this is the imaginary part of this expression. We will equate the imaginary part to 0 to find the frequency of oscillation. The imaginary part is HIE into minus 1 by omega C1 minus 1 by omega C2 plus omega L equal to 0. Here HIE cannot be 0. So this term is equal to 0. These two terms are brought to other side, so they become positive. We'll take 1 by omega commonly out between these two terms. It becomes 1 by omega into 1 by C1 plus 1 by C2. We'll bring omega to the other side. So it comes in multiplication. Omega square L is equal to 1 by C1 plus 1 by C2. We'll find out omega square from it. Omega square is equal to L comes as 1 by L into 1 by C1 plus 1 by C2. We'll replace 1 by C1 plus 1 by C2 by 1 by C equivalent. So it becomes omega square is equal to 1 by L into C equivalent. When we take square root of it, we will find omega equal to square root of 1 by L into C equivalent. We'll replace omega by 2 pi F and find F, which is equal to 1 by 2 pi square root of L into C equivalent, where C equivalent is equal to C1 C2 into divided by C1 plus C2. This is the frequency of oscillation of Colpitts oscillator. This is the real part of the general expression which we made it equal to 0 to find the condition for oscillation. The first term and last terms are brought to other side, so they become positive. We'll take 1 by omega square C1 C2 commonly out between this and this term. When it is taken out, it is written as 1 by omega square C1 C2 into 1 plus h of E. We'll cancel C1 on both sides and we'll bring omega square C2 to the other side. Then we will write L into omega square C2 equal to 1 plus h of E. Here omega square is replaced by 1 by L into 1 by C1 plus 1 by C2, which was found in the previous slide. Here L is carried over here. For omega square, 1 by L into 1 by C1 plus 1 by C2 is substituted. C2 is carried over here is equal to 1 plus h of E is written as it is. These L's are getting cancelled. Then 1 by C1 plus 1 by C2 into C2 is written, which is equal to 1 plus h of E. We'll bring C2 inside. C2 by C1 plus C2 by C2 is 1, which is equal to 1 plus h of E. We'll cancel 1 on both sides. H of E equal to C2 by C1. This is the value of h of E required to satisfy the condition for oscillation. Advantages. Colpitts oscillators produce pure sine wave because the capacitors provide a low reactance path for the high frequency signals. They can withstand high and low temperatures. Frequency of oscillation can be varied by using two variable capacitors. Very few components are sufficient to design a Colpitts oscillator. The amplitude of the output remains constant over the working frequency range. Disadvantages. It cannot be used as a low frequency oscillator because high value of inductors are not possible practically. It is hard to design, difficult to adjust feedback as capacitors are to be changed. It has poor isolation property. Applications. Colpitts oscillators are used to generate pure sine wave with high frequencies. They are used as a temperature sensor with a surface acoustical wave resonator. They are used as a local oscillator in radio receivers and also used as RF oscillator. Used in microwave applications, broadband communications and spectrum spreading. Used for the development of mobile and radio communication systems. They have many applications used for the commercial purposes. Thank you.